Welcome back, everyone. This is Dr. Gallenstein, and here we are with the RStudio demo for lecture number 10, randomization. So in this demo, I just want to go over all of the skills that we need for doing analysis of data when there has been some sort of program or intervention that has been randomly assigned, right? So when we have this randomization, it gives us a strong ability to conclude that we do not have omitted variable bias, and so we can get a causal estimate of the impact of some intervention. So here I just want to show you in R how to run all of the commands that you need to perform the analysis when you have data when the intervention was randomly assigned. So when you have an independent variable that was randomly assigned. Okay, so let's jump in. So typically we'll load some libraries, import our data. Data set's another variation on that wages data set. I'll use wages random here. That's the name of the data. I'm just going to call it wages. That's the name I'm going to give it when I import it. Okay, so as you know, one of the first things we need to do when we have randomization is we need to perform some tests that will allow us to validate that the randomization achieved what we call statistical independence. So that's statistical independence. That's where the variable that represents the randomized intervention is not correlated with other variables. Right, and so if it's not correlated with other variables, then it's not going to be correlated with the error term, and so we will not have omitted variable bias. And so what we do to test that is we will do a balancing test. So a balancing test is an informal test, and what it consists of is just doing a t-test for a bunch of variables in the data set where we compare the average value of the variable for the treatment group, the one with the intervention, to the group without the treatment or without the intervention. So that's what we're going to do here. Very quickly, I'll just open up the data set. We'll get a feel for it. So we've got the wages variable. We've got a bunch of other independent variables here. And we have this treatment variable. And we're just going to say this treatment variable, it equals 1 for those who've been randomly assigned to participate in a training program that is supposed to help people improve their wages, and 0 if they were not randomized, not randomly assigned to receive that treatment. So the training, I should say. And this treatment variable was randomly assigned. So because it was randomly assigned, it should be uncorrelated with the other variables. That is, the people that are in the treatment group should be the same on average as the people that are in the control group. So we're going to test that using a balancing test. So all we're going to do is just a series of t-tests where we compare some of the other independent variables with, we're going to compare them between the treatment group and the control group. All right, and what we're looking for here is we're looking to validate the assumption that the randomization achieves statistical independence. So when we run these t-tests, we're going to look to see are any of these significant. What we want is at least in terms of getting evidence for statistical independence, what we want to see is that there is no difference, so that the difference between the treatment group and the control group is not statistically significant. So we're actually hoping for no statistical significance here. If there is statistical significance in these t-tests, that would be evidence against the assumption of statistical independence. So let's just do one at a time. So here we've got the education. So what we're doing here is we're calculating the average education level for the treatment group and the average education for the control group, comparing that average education. And what we hope to find is that on average, these two groups have the same level of education. So let's check it out. So here's the average education level for the treatment group, average education level for the control group. You can see that numerically they're very similar. There's a small difference. Let's see if that difference is statistically significant. We'll look at the p-value. We'll see that no, it is not. That p-value is well above any of the standard thresholds for statistical significance. So this is not statistically significant. That's good. Now let's run that for the rest. All right, well, we have experience here, non-white, female, married. Let's run all of these and just see. So we'll just look through. We're just going to quickly skim through to see if any of them are statistically significant. So we already did this for education, so no. Experience, no. Let's see, non-white, no. Female, no. Married, no. Okay, so none of these are statistically significant. There's no statistically significant difference between the treatment group and the control group that we can see here. That's good. That supports our assumption that the randomization achieves statistical independence. So that is that the treatment variable is not correlated with any other variable. If the treatment variable is not correlated with other variables, then that treatment variable will not have omitted variable bias. So now that we've done that, now that we've validated that assumption, let's go ahead and run some models. So what I'm going to do here is I'm going to run two models. The first one I'll call model 1, and it's just going to be wage regressed on the treatment. Now, oftentimes we include many control variables or other independent variables, but when a variable is statistically independent, then we don't actually need to include other variables. So here I'm just going to do model 1. It only has the treatment variable. Now, from previously in the class, having only one variable, that would raise red flags about omitted variable bias. But because the treatment variable was randomly assigned, we don't need to worry about omitted variable bias because this treatment variable is not going to be correlated with the error term, even though there's no other variables in the model. So we'll just go ahead and run that. And then I'll just go ahead and run another model that adds a few other independent variables. But like I said, they're not strictly necessary in this case. So it's model 1 and model 2. And I'll go ahead and run the summary for these two. You'll notice here that I'm using robust equals t. So I'm just going to go ahead and use those robust standard errors just in case there's some heteroscedasticity. And so now when we check out our model, we can see here's our treatment variable. It is statistically significant. It's statistically significant at the 5% level. That's what this means in R. And we can go ahead and interpret this. I'll just interpret this for practice. So because this treatment variable was randomly assigned and because the balancing test checks out, that is, it supports the assumption, I'm going to go ahead and comfortably assume causation here. And so I'm going to say that receiving this soft skills training, that was the training, so the treatment, that was the intervention. So receiving this training increases wages by 56 cents per hour. Let me interpret it again. I'm going to really emphasize the causality here. So we can say that the soft skills training causes people's wages to go up by 56 cents per hour. So you see here, when I am able to conclude causation, I actually use the word causation in the interpretation. I really want to emphasize that. And I want to be clear in the interpretation that I give that I make the distinction between a coefficient that can be interpreted causally and a coefficient that cannot. So here I just want to use the word causation here to make that clear. All right, so there we go. There's the first one. I'll just use Stargazer here to produce a nice table. Now, one thing that we'll see here is that, so one way of kind of looking for some potential bias is by comparing the coefficient when you run the model without other variables and when you run the model with other variables. So even though we had good evidence for statistical independence from our balancing test, we can see here that by comparing model 1 and model 2 that there actually is a decent amount of difference between these two coefficients. It's not huge, but it does, it might raise a little bit of suspicion that there might still be some omitted variable bias despite the randomization. But you'll also see that this coefficient here, this 56, is statistically significant while from model 1 it is not. One advantage of adding additional control variables is that adding those variables can help to reduce the standard error. So you see the standard error here. And so when we reduce that standard error, we increase the chances of seeing a statistical effect, statistically significant coefficient. So here, there's a little bit of a difference. It's not huge, so it's not a huge red flag. but it's a little bit different, a little bit more than I might expect. And so that might indicate to us that this treatment variable might not have perfectly established that statistical independence. Okay, so I just want to take a look at that. All right, so next, let's talk about the other kind of, the other thing you can come up with randomization. So sometimes when we implement a randomized experiment, we will randomly assign people to receive an intervention, but there might be some imperfection in terms of who actually receives that intervention. So in this case, we've randomly assigned people to receive some training, and we're hoping that that training will improve their wages. But it's possible that maybe some of the people that were randomly assigned to receive the training didn't actually receive the training. And likewise, it's possible that some of the people that were randomly assigned to not receive the training managed to receive it anyways. That would be called imperfect compliance. So here I'm going to show you how to check for that. So let's generate a table. The table is just going to be a 2x2 table. On one axis we'll have the treatment variable, and then from the wages data set, and the other axis will have the training variable from the wages data set. And we'll just be able to check for that imperfect compliance. So here we have the table. On one axis we have the treatment variable, the other axis we have the training. If there was perfect compliance, we would expect that all the observations of the data set would either be in this 0, 0 spot or in the 1, 1 spot, indicating that everyone assigned to the control group did not receive the training and everyone in the treatment group did receive the training. But that is not what we find here. We find that some people assigned to the treatment group did not receive the training. And we find that some people assigned to the control group did receive the training. And so what we have here is imperfect compliance. Now, when we have imperfect compliance, we actually run the same models. So I'm just going to rerun the same models and show the result. Okay. But when we have imperfect compliance, we interpret those results differently. When we had perfect compliance, we interpret the coefficient as an intent to treat effect. When we have imperfect compliance, we interpret it as what we call an intent to treat effect, the ITT, the intent to treat effect. And we know that that intent to treat effect, that ITT, is going to be an underestimate, or a more conservative estimate, we should say, than the ATT being the average treatment effect. Okay, so that's just how you run all the models in R. I hope you enjoyed the lecture, and I'll see you next time.